Wait, but he said that you. My teacher said that you don't need the external field for the railgun. The rod does not get pushed by its own magnetic field. The current carrying wire feels a magnetic force only from an external magnetic field at its location, not from the field it creates within the simple IL cross B case. So with battery rail sliding around, no external B, you do not get the usual railgun. In a railgun, the current in the rest of the circuit, especially the rails, creates the magnetic field that pushes the rod. All right, so to build a railgun, current in the rest of the circuit, especially the rails, creates a magnetic field at the armature rod that pushes that, and that field pushes the rod. All right, so the system is the rod and okay, but I mean, come on, it's like the same as shit. All right, B rails, I get it. All right, so it's subtle. It's like a subtle point, but you know. All right, here the best one sentence fix. The current in the rails and the rest of the circuit creates a magnetic field at the rod that pushes the rod. Okay, good. Simple, actually. All right, let's get to doing some problems. Okay. We did this sort of. All right, let's close all this. Let's get fresh. You know, let's get fresh. Let's get froggy fresh. What is that? Froggy fresh? I have no idea what that is. Okay, we did this. This was actually really easy. Here we go. This is the one we're doing. I think this is 97. Okay. Let's draw it. We have a rod, length L. V initial is equal to 0, but we have a constant acceleration A. This is a distance D for my resistor with resistance R. This is D, and this has mass M. Now the question is, when rod has traveled D, how much charge has flowed through resistor? This problem is incredible. Okay, so first let's find V of t. V of t is equal to VI 0 plus 1/2. No, I think it's just AT plus AT, right? Yeah. Okay, so A is given, so V of t is equal to A times t. And what we want to know is we want to know epsilon of t. We want to know the voltage, because if we find the voltage, we can't say voltage. if we can find the EMF as a function of time, then we have the current as a function of time. And then we can integrate dq dt. And it's a separable it's a separable diffeek. So epsilon of t is equal to minus d phi b dt. Now the change in flux. So let's think about this. Oh, and do we have an external B field? We must. Yeah, B is into the page. So first off, let's just calculate what is the flux at time 0. Flux at 0 is going to be, and this is where I get kind of confused because, all right, so let's just expand the definition. So the flux is the integral, the surface integral of B vector dot dA n hat vector. So we need to make a choice. So we're going to say that the normal is minus k hat also. So that the magnetic field and the normal are the same. So we're going to get that IB is equal to BLD. Okay, so we have the at t equals 0. So we have the flux through this open region. But we want to know how the flux through the region is changing. And it has to be decreasing. So we need to take d flux dt. So B is constant, L is constant, but D is changing. So let's find, okay, if we know the velocity, well, we can figure out the position too. Is the yeah, so delta x is going to be equal to 1/2 at squared. Okay, so the change in D should be D minus 1/2 at squared. Or this is the, like, distance left. So the flux will be a BL times D minus 1/2 at squared, and then all dt. So we let D be at like an actual constant. So we're going to get BLD minus 1/2 BLAT squared. So this goes to 0 when it's the, ddt. But this is going to be minus BLAT, blat. So this is going to be the change in flux with respect to time. Oh, which is just minus BLV. Okay, I kind of, because he probably even gave you that. Okay, he didn't, but I guess I just derived it. But in any case, it's very easy. So this is the, okay, so now we want minus D, okay, the minuses cancel, so the, yeah, so the change in flux, wait, actually, no. Wait, hold on. I'm trying to figure out the minus sign. The change in flux is decreasing. That's true. So minus d flux dt is equal to BLV. So this is equal to epsilon. So BLV equals the electromotive force. BLAT. Sorry, let me just pull up my channel. Okay. All right. So if we know the voltage is a function of time, then we can do Ohm's law. V is equal to I times R. So we're going to get BLAT is equal to the current times the resistance, which is equal to dQ dt times R. So BLAT dt is equal to dq. We integrate both sides, and we just get BL. Oh, and we have to integrate from. We have to figure out what the. So we need to solve for d is equal to 1/2 AT squared. So d 2d over a square rooted is equal to t. So we need to actually integrate from 0 to square root of 2d over a. All right, so now we're just gonna plug in. So it's gonna be t squared. So is it BL a 2d over 2a? Is it just gonna be BLD? There's no freaking way. It's just BLD. Oh wait, where's the R come from? Oh yeah, the R. It really is just that, dude. That's so funny. What is R? The resistance? Damn, I did so much work for this problem, and it was actually like a piece of cake. Faraday's law is definitely the coolest one. Did he solve for this thing? Okay, he did. That's what I thought. It doesn't matter how we move. That is crazy, actually. You'd think it does, but it doesn't. Okay. All right, I wanna practice writing up one of these ones. Okay, so we have a bar length equal to L, mass equal to M, VI equal to 0. On a circuit with distance D a circuit with width, distance d, and resistance r. So we have a bar, length L, let's just say, vertical, mass m, vi equal to 0 on a circuit with width, distance d, and r. Just say left side with distance d, bar given acceleration equal to a I hat, b vec is equal to minus k hat b. Okay. Is there anything else we need? What is the total amount of charge that passes through the resistor when the bar travels after the bar travels distance d? Okay. All right, so I think we set up the problem. Now this is what we do. We say what is V of t? V of t is equal to Vi plus AT is equal to AT. X of t is equal to x0 Oh no, this is Vi. Okay, so we have the position of the bars and the velocity of the bar as functions of time. Now we want to know what is the EMF as EMF of t. So EMF is equal to minus d flux b dt. What is flux b? Flux b, let's just say flux of t at 0 is going to be equal to integral of b vec dot dA n hat. Let's choose the normal to be minus k hat parallel with b vec. Then we're going to get is equal to BA is equal to BLD. So now, but how is the flux changing respect to time? B and L constant, but D isn't. D minus x of t is equal to the width is equal to d minus 1/2 at squared. So d flux dt is equal to bl times ddt bl d minus 1/2 at squared. All right, let's just, what's the answer? It's going to be minus bl at. See that the flux is decreasing. Good. Good. This is also equal to minus BLV. See the standard. So then, so minus d flux dt is equal to BLAT. To BLV. All right. So yeah, we're doing it the long way because you can just remember the BLV equation, but like it seems kind of lame considering how easy it is to derive. All right. So now that we have the EMF of T, do we? Yes, because so EMF of T equals BLAT. We can apply Ohm's law to derive the all right, so EMF of T is equal to I of T times R. So I of T is equal to BLAT over R. dq dt is equal to BLAT over R. dq is equal to BLAT over R dt. Int dq is equal to int BLAT over R dt. But what are the bounds? We need to make sure that the rod distance traveled is d. So we can say go back to this is equal to 0. So we find when x of t equals d. T is equal to square root of 2d over a. What do we put for the bounds here? I don't know what we put there. But anyways, we get BLD over R. So as the resistance increases, the charge decreases. Yeah, I see chat. Yeah, I don't look at chat the most, but when I finish the problem, usually I look at the chat. All right, solution's right. Your bounds on the integral are right. But what do the correct bounds are? Yeah, but what on the left side you can either write 0 to q or just q. Okay. Oh, that's actually smart. Yeah, you could do 0 to q. I think that makes sense. So, int 0 to q. All right. Sounds good. All right, next problem. That problem was pretty easy. Let me just put in my spreadsheet. 97. Not that. It's a emotional EMF problem. Basically, use kinematics. And motional, yeah, to find a charge. Integrating a basic diffeq. All right. Chill beans, chill beans. All right, here we go. Circuit problem. I love a good circuit problem. Who doesn't? All right, this is 3. So we got a source. We got a fully charged cap. We got a resistor. We got another source. This is 30. V2, V1. Okay, these are connected here. Then we have a resistor, then another resistor in parallel. We're going to ground this node, connect these together, connect this together. Okay, so this is, C full, capacitor is full, R1 is 10, R2 is 10, R3 is 10, and R4 is 10. Okay, let's just solve the circuit and then we can figure this out. So this is 10 volts and this is 30 volts. So first off, I'm just going to go ahead and start labeling. A, B, C, D, E. Okay, 5 nodes. The graph has 5 nodes. Okay, let's just write this out. V1 connects D to A equal to 10. C1 connects A to B equal to C. That's fine. R1. Oh wait, let's do V2 connects D to C equal to 30. All right, R1 B to C is 10. R2 B to E equals 10. R3 from E to D equals 10. R4 E to D equals 10 also. Okay, so this is clearly going to be, what is it? It's 1 over R tot is equal to 1 over 10 plus 1 over 10 is equal to 2 over 10 is equal to 1 over 5. R tot equals 5. All right, so we have a 5 ohm resistor there. So we can already reduce the IC equal to 0 full. So only one closed loop. All right, so let's rewrite the circuit. Boop, 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 boop. Resistor, resistor, resistor. Okay, and then we have this is ground. Oh yeah, let's ground. So we're going to call this. So E is grounded. So ground E. Okay, so now we have one loop. And I think he likes doing these problems where you do KVL. So KVL, we're going to have 30 minus, let's call this R1, R2, and R3. This is going to be 10, 10, and 5. So 30 minus VR1 minus VR2 minus VR. Let's not call this 3. Let's call this parallel. Parallel. VR parallel is equal to 0. So we have our Kirchhoff voltage loop. So this is going to be minus I times 10 minus I times 10 minus I times 5. So we're going to have 30 over 25 is equal to I, which is 6 over 5 amps. So now that this is ground, we know that I is going this way. So 0, so VR parallel is going to be, let's call this A, B, C, D. It's going to be VD minus VC is equal to 6 over 5 times 5 ohms. Okay, so there's 6 volts. So D is at minus 6 volts. Then this has to be at, wait, isn't this this is 30 volts. So so 30 minus 6, 24 volts. And then this, okay, what node do I want to find? This node? Oh, interesting. Well, the voltage across, C is equal to Q over V, right? So V is equal to Q over C. So we found though that this is minus 6. Oh, okay, so VA is equal to 4. Easy. All right, finish the problem. Come on. This is a basic circuit. If you can't do this, something's wrong. Take a screenshot. Figure it out. Basic 1 current circuit. See that cap has no current, then reduce the parallel, then KVL. Easy. Come on, do it in like 1 second. I'm not even gonna write this one up. This one's so easy. All right, 82. Ooh, okay, these are good ones. This is gonna be a good one. Find the magnitude of the induced electric field at a distance r from the axis of the solenoid shown in the diagram. Recall that the uniform magnetic field inside it is that. Let the current through the solenoid be increasing linearly. Okay, all right, great, awesome. Okay, so we have a solenoid and we got loops. The B is equal to minus K hat mu 0 I of t, and this is going to be B of t times n. So B of t is equal to mu 0 c t n. Okay, now we want to know the flux though. So this must be given a radius, r, capital R. Okay, so the flux, magnetic flux is going to be B dot dA. Okay, we're going to choose the normal. Normal is minus k hat. So we got parallel things there. So it's uniform spatially. Okay, so we're gonna get that the flux is equal to B of t times A equal to B of t times pi r squared, which is equal to mu 0 c t n pi r squared. Now what we want to do is just take d dt minus d dt, which is going to give us minus mu 0 c n pi r squared. So this is the change in mag flux. Okay? So if we know the change in the magnetic flux, then we know the closed line integral, and let's see, distance r, so we got this thing r. E dot dl by sim const mag fixed r. So, and this is parallel. E is parallel to dl because if radial, then perpendicular, but flux change non-zero. Violate Faraday's law. But also cylindrical sim implies E is equal to E, where this is azimuthal. But by Lenz law, E opposes d flux. So the change in flux is increasing. The d flux increasing. So E oppose the increase. So it's going to be this way. So it's got to curl, so counter clock. Okay, so we know now so here we go. So we're going to get 2 pi little r E is equal to minus mu 0 c n pi r squared. It says find the magnitude, right? Yeah. So E is equal to minus mu 0 c n pi r squared over 2 pi r little r. The pi's cancel. Okay, that should be it. R squared mu 0. I got a minus sign, but I don't know where the minus sign came from. All right, so I'm gonna write this up because we gotta get to the bottom of these minus sign problems. But I think I got it right. All right. So wait, did I get it all right though? My mu 0 n c r squared over 2 r. Okay, good. Magnitude. Okay, yeah, magnitude. So he took the absolute value there. Okay, I got it. Okay. Solenoid radius r, current I of t is equal to c t, c constant. Find magnitude of E distance r away from. You know, you should pay attention to this. When people learn a cool sounding word that makes them sound really smart, they'll use it a lot. Me, myself included. Azimuth makes you sound so smart, but nobody knows what the hell you're talking about. It would be much easier if you just said tangential, you know. But I mean, this maybe is more precise, but nobody knows what you're talking about. I did this. Did this. All right. Okay. All right. I feel like I don't want to write this up. Do we need to write this up? Let's just keep going. I just kind of like doing the problems. I feel like if I meant away from. All right, let's just do the solution really quickly. It's just b of t is equal to mu 0 I of t n is equal to mu 0 c t n, or let's say n c t. Okay, but we want d now, so flux equal to b of t a, do the integral. You get equal to mu 0 nct pi big R squared. So then d minus d flux dt is equal to minus mu 0 nc pi r squared. So then which is equal to c int closed int e dot dl, but then show E must be tangential for dot to be good, and must be tangential by Faraday's law and cylindrical symmetry. Okay, so then we get and const mag at fixed r. Okay, so we get E times 2 pi little r is equal to minus mu 0 nc pi r2. Okay, then you get E is equal to only mag asked take abs. Okay, E is equal to mu 0 nc pi r2 over, wait, let's cancel r2 over 2r. All right. This is just what did we just do? This is a time varying current. Find the flux and the time varying current through solenoid. Find E of R. All right, problem 20. Circuit problem. Refer to the diagram. Given an ideal battery of voltage V, connected in series with R1 and R2, of course, there will be some voltage across R2. However, now consider that a load resistance like a voltmeter RL is connected across R2, and now there is a voltage across RL that is the same as R2 because the two are in parallel. But this voltage across RL is not the same as the original voltage across R2. Before the voltmeter was connected. Find the ratio of the original voltage across R2, call it V2, to the new voltage across R2. Find the ratio of the original voltage across R2, call it V2, to the new voltage across R2 after the load is connected, call it V prime 2. Your final answer will be in terms of R1, R2, RL only. For full credit, your final answer should be arranged such that it's easy to see that as RL approaches an infinite value, then the original voltage across R2 is the same as the new voltage. Also briefly state in words whether the voltage across R2 increases or decreases after the load resistance is placed across it. Oh, that's a tough one. This is pretty interesting. All right, this is definitely takes some thinking. So first off, V is equal to IR. So I is equal to V over R1 plus R2. Okay, so first off, let's just find R parallel is equal to 1 over R parallel is equal to 1 over R2 plus 1 over RL. We're going to get RL plus R2 over R2 RL is equal to 1 over R parallel. So then R parallel is equal to R2 RL over RL plus R2. All right, so we have the parallel resistance. And what we're trying to find is find the ratio of VR or V2, so we call this V2 voltage across R2. Find the ratio of the original voltage R2 divided by V prime 2. I'm gonna get some water really quick. So wait, the voltage across the... So, but then, I prime is gonna be V over R prime, which is equal to V divided by R2. Oh, but it's gonna be the sum. So wait, so R prime is gonna be equal to R1 plus R parallel. So R prime is equal to R1 plus R2 RL over RL plus. So so V prime 2 or V2 prime is going to be I prime times R2 prime. So it's just going to be V. Wait, but R2 prime is some annoying thing. Yeah, this is R2 prime. Bro, it's so much algebra. Alright, let's just finish it. Whatever. Oh, because this is not. This is no. This is our total. Our parallel is what we want. This is not. This is our parallel. So this is going to be R2 RL over RL plus R2. So this is V2 prime. Did I even get anywhere close to the right answer? Okay, I got this right. V2 prime. Let's see, what did I get? I got V R2 RL over R1 RL R plus. How do we know that V2? So I probably got the number, but I don't know. There's probably a little bit more to do here. You know, how do you know that this is less than one? Okay, so I'm just gonna let's just keep going. Like, that's just algebra, bruh. I mean, it would be good to do weird ratio voltage divider thing. Hard part would be good to do. It would be good to do right up. All right, 89. All right. Starting from Faraday's law, find the induced EMF in the rotating conducting bar. The bar is pivoting about one end, and its total length d, its angular velocity omega is given. All right, so we have some bar. Okay. It's got omega, length d, no mass given. It's conducting. Conducting. Here's a pivot. And what do we want? We want to say find induced EMF. Oh, and we have a B field into the page. Okay, I don't want to see the solution. I don't want to see the solution. It says starting from Faraday's law. How do you even do this? What is the flux? Oh, yeah. So we need to find the flux. What is dA? His diagram is so garbage. Oh, man. All right, so this is kind of challenging, actually. What is R? He means D. Yeah. Wait. So delta area, the change in the area with respect to theta is equal to d squared over 2. dA dt delta t the change in theta with respect to time, this is omega. All right, so we get d squared 2 omega is dA. All right, that one is induced. This thing is moving along. Yeah. Oh. All right. Yo, what's up, Lemon Leaf? When did you post that? I don't know when you posted that. I'm back. All right, let's lock in this. This one is like really weird Faraday's law problem. I don't even know what to do with that. Okay, this one says coolest one yet, 43. Okay. I don't know if I'll agree with the coolest one yet. Say that a charge Q has velocity. Say that the charge is in a B field and there's no electric field present. In the reference frame of the charge. Okay, let's do this thing. Okay, so we have Q with V equal to 5, 0, minus 2. And B is equal to minus 3 K hat. And there's no electric field present. E equal to 0. In the reference frame of the charge where it is not moving, find the... Okay, so you just apply FL is equal to Q times E plus V cross B. So then let's do the cross product. IJK V cross B 5 0 minus 2 0 0 minus 3. It's gonna be minus J hat times minus 15 meters per second. So 15 J hat is equal to, it's not meters per second, it's gonna be like newtons, right? So therefore, or actually no wait, this is not in newtons, this is newtons per coulomb. $15. Oh, find E? Yeah, okay. Same thing. So easy. Not the coolest one yet. Easy problem. Frame of reference change. Lorentz force. Okay, 13. All right, circuit problem. I hate how these are drawn. I'm just going to look at this, draw it, and then solve it. Okay, let's solve this thing. I hate how he draws these, because he kind of gives you a lot of answers in here, but I'm going to try to avoid looking at anything I can. All right, R1, R2, R4. Then we have a resistor that's dead. It's grounded. And then what is that? Is that a potential? Or that's a source. Okay. We got a source here. And we got another resistor here. And then we got a capacitor here. Okay, so I'm just going to okay, so V, okay, they're trying to find this and this. All right, I'm going to label it however I want. A, B, C, D, E, F, and G. Okay, so I found 1, 2, 3, 7. Yes, I found 7 nodes in this circuit. And so what I like to do is I like to write out very systematically all of the equipotential surfaces, and then all the actual graph. So we're gonna have okay, wait, I have to write down some numbers. So V1 is equal to 12, R1, R2, R3, R4, V2 is equal to 6. All the R's are equal to 2 ohms. R5. Okay, 1, 2, 3, 4, 5. Okay, good. And then this is C full. It's fully charged. All right, so V1 from G to A is equal to 12. V2 from D to E is equal to 6. R1, A to B equal to 2. R2, B to F is equal to 2. R3 from B to C is equal to 2. R4 from B to D is equal to 2. And R5 is R5 from E to F is equal to 2. And then C from F to G is equal to C. All right, so we've written out all of the, oh yeah, and then ground C. Okay, so R3 dangling, no loop, I equals 0. So V of C equals V of B equals ground. Okay, so we found B is 0 volts. Okay, now see that C is full. So I R1 equals 0. V1 supply, no charge. Okay, so this source is supplying no charge. So then we've reduced this problem into a single circuit. So the circuit can be made into one loop. Okay, so let's do it. So we have R2, R4, this is ground, this is the supply, 6 volts, this is the resistor, and that's it. And what are we trying to find? We're trying to find V of G and V of F. Find G and F. So this is, so I'm going to relabel this now. This is going to be A, R1, R2, R3, B, C, D. All right, so we have 4 nodes in the reduced circuit. So we're going to get KVL. 6 minus R, 6 minus V, R3, minus V, R1, minus V, R2 is equal to 0. Okay, so this is going to be 6 minus 6 I is equal to 0. I is equal to 1 amp. Okay. So since this is dropping lower, this is 0 volts. So now VR2. So since no current is going through here, Okay, I got it. All right, so the voltage across VR2 is going to be V equals IR. So I is equal to 1, R is equal to 2. So this is going to be minus 2 volts at B. So then this is going to be 4 volts. Okay, then this is 2 ohms. So we're going to do, 1 amp times 2. This is going to drop to 2. All right, so V of G, which is V of G equals 2. Then this is going to be A is 0. So then, oh wait, no. V of G is equal to minus 12 volts. And V of D, which is F, is equal to 2 volts. All right, my answer is minus 12 and 2. So A is 2, and this is minus 12. Wait, 14. Wait, what did I do wrong? No, I don't think that's right. Oh. Oh, okay, wait. He's asking for question was V cap, which is going to be, minus 12 minus 2 is equal to minus 14 volts. Okay, I get it. But that's a detail, man. That's like not conceptually a stretch at all. We're not freaking out about that. All right, so next problem. I mean, come on, we just got to keep doing them. One after another after another. All right, so this is again, reduce circuit, reduce to single loop, find current, find drops, route around the cap. Easy. All right, let's see. 26. I don't remember this one. Oh, this is a good one because I don't remember this stuff at all. All right, so we have a washer. All right, we have a washer. It's spinning with omega. So this thing, like this is like this. So omega is like this. Actually, the weird thing is that this one spins this way and this one spins this way. I'm gonna make it. I'm gonna make it spin counterclockwise. So that means that W equals WK hat. So then this is an I K J kind of thing. So then this is I J. Okay, now the inner radius, what is A? Yeah, the outer radius is B. That's good. And now, what is the question though? The question is, in the diagram, a spinning washer of total charge. Okay, so let's give it a charge. Okay, so this thing has Q is spinning about plus K. Find the magnetic moment vector of this spinning washer. Okay, so we're given mu is equal to IA. So that's the current times the area. Also, find the direction of the torque applied to this spinning washer in terms of the external magnetic field indicated in the diagram. In one and only one sentence, describe what the spinning washer will begin to do when first exposed to this magnetic field. Tau is equal to mu cross B. I find moments quite hard to understand, personally. Okay. So we're going to write this problem up. Definitely. Okay, so B... Oh, shit. Okay, B is equal to B0J. Okay, we got this. Got this. The diagram is set up. So I am totally blanking on how to do these problems. Well, let's just start talking and see where I can get. So, what we imagine is a bunch of little loops. And so if you take a little loop, a tiny little loop, and it's spinning with omega, then the current through there we could say, the current is going to be equal to, I guess a dq, a small amount of charge, well, okay, wait. First off, omega times t is equal to the angular velocity times the period should be 2 pi, right? Because it's an angular velocity, it's not going to be a circumference. It's just going to be it's just going to be in radians. So the angular velocity times the period is 2 pi. So t is equal to 2 pi over omega. Then the current is equal to dq dt. So the change in the q is change in time. So we could put, delta q, which should be, the surface charge density or something like sigma times, 2 pi r or something. I don't know. You have to derive you probably have to derive the dq, or I actually don't know how you do that. But you're going to get delta q omega over 2 pi. This is the current. You know, the reason why this is hard is because I don't understand moments. Sigma omega RdR times pi r squared from A to B. Oh, actually, I was like right there. What is a moment, dude? What are moments? Okay, so if I see this thing, let's first find, so it's going to be pi b squared minus a squared is equal to a, area of washer. Okay, so that means that q over a is equal to sigma is equal to q over pi b squared minus a squared. And now dq, or wait, hold on. So now we want mu is equal to the integral of a di. The change in current So the current changes. So for a current, you need a little loop. That is maybe one thing to note. So we need a little loop. So that loop must have an area. So it's going to be, you know, so so first off, the charge on a little loop will be, sigma times 2 pi r dr. The charge on a little loop will be sigma times 2 pi r dr. The current is dq dt. It's the amount of charge flowing. Okay. Now the amount of charge flowing, let's go back to the problem here. The amount of charge flowing will be this amount of Q, will be Q per revolution time. So Q over T. So we know that omega T is equal to 2 pi. So T is equal to omega over 2 pi. 2 pi over omega. So then, sigma 2 pi r dr divided by 2 pi times omega. 2 pi's cancel, and we're left with sigma omega r dr is equal to di. So then mu is equal to the integral of a sigma omega r dr, but then a is going to be equal to pi little r squared. It's the area of the loop. And we're going to integrate that from, so we're going to get from a to b pi r cubed sigma omega dr. So we're going to get, pi, we have to unwrap sigma, do we? No, we don't. Well, we can. Pi q, pi's cancel. Pi b squared minus a squared. Oh yeah, I remember this problem now. Omega integral a b r cubed, okay, goes to r4 at ba is equal to b to the fourth over a to the fourth. Oh no, b to the fourth over 4, so 1/4 times b to the fourth minus a to the fourth. So we're going to get q omega over 4. And then the interesting part here is that the b squared minus a squared, you can actually factor out of the thing. So it's going to be b squared minus a squared times b squared plus a squared. These cancel, and you get q omega b squared plus a squared over 4. And that is the magnetic moment. And now the magnetic moment has to be in line with the velocity, the angular velocity. So I got that. But now we need to find the torque, right? Find the direction of the torque. So tau is equal to mu cross b. So b is a j hat. So I, j, k, b. Wait, where did I say b? Oh, I don't have b in here. B is equal to b j hat. So we have 0, b, 0, 0, 0, 1. So so it's an I hat. So tau is plus I hat. And what that means, let's say if I say the torque is an I hat, but the loop is sitting here with K hat pointing up, let's say I hat this way and J hat this way. You know, mu cross B. Wait, I did this wrong. I did this totally wrong. This is 1 B. It's mu cross B, not B cross mu. So this is actually going to be minus I hat. But what does that mean? Does that mean that the... Okay, I gotta go to the bathroom. I'll be back. Okay, so what was the solution to this problem? It was remember that when you're finding a magnetic moment, you're going to be adding up a bunch of small loops of current. So that's really the key to magnetic moment problems. Remember that you're adding up small loops of current. Okay. So di to dt in the meaning of torque. I mean, this is definitely the hardest part, but the key to starting the problems. So let's do we have 26? Okay. So let's say, okay, so we have a washer in XY plane, IDA, ODB, total charge Q, angular velocity W. I'm going to put W. I'm not writing omega. That's insane. Equal to, so W vec is equal to W K hat. There's a B field. B is equal to B vec is equal to BJ hat. I believe that's everything. So the problem is find the magnetic moment mu, then find the torque direction and explain what that means. Okay, solution. The key to finding moments, magnetic moments, is to remember that the task is to add up a bunch of small current loops, which must be in the form of loops, because that's what current is. All right. So first, quickly derive the surface charge density sigma. So Q over A is equal to sigma. A is equal to pi. Oh, the area is equal to pi times B squared minus A squared. So sig equals Q over pi B2 minus A2. Okay. Then write down mu is equal to int d mu, which is equal to int a di. But what is di? It's a small current loop. Imagine that we have a loop with thickness dr, so circumference 2 pi r, then the amount of charge on that loop will be sigma times 2 pi r dr. But we don't want the current, we don't want the charge, we want the current. Current is coulombs over, or Q over time. So we know the angular velocity omega. So define t equal to the period of you know, whatever. So then omega times t is equal to 2 pi. So t is equal to 2 pi over omega. So the charge q over t is equal to, you know, sigma times 2 pi rdr divided by 2 pi divided by omega. We can simplify this. The 2 pi's cancel. You get sig omega r dr. I think that's the whole thing. So this is the current through di. That is the current di. So a little piece of the current going through this spinning washer is di. I gotta cut my fingernails. These things are bothering me. No. That seems good. All right. So that is the current di. The magnetic moment is the product of the area enclosed by the loop and the current, the loop current. So A is equal to pi r squared. So then mu is equal to int pi r squared sig omega r dr is equal to, you know, let's just pull out the pi sig omega int r3 dr is equal to, you know, is equal to, oh yeah, and this has to be integral from a to b, all right, so this is going to be, you know, let's just do this. B4 minus A4 is equal to pi, and then sigma is going to be Q omega B2 minus A2 B2 plus A2. I'm just doing the simplification. This is actually stupid. Q over B2 pi B2 minus A2 is equal to Q omega B2 plus A2. Oh, 4. Let's see, was I right? Yeah. Oh yeah, and K hat. The direction of the magnetic moment is I don't think this is always because all right. So the mu is K hat and B is and what the hell? And B is J hat. So tau torque is minus I hat, which I believe means that at the first instant the spinning disk will turn to spin pointed along the spin with its axis pointed toward minus I. Okay. Okay, I actually that was good. 101. Refer to the diagram. A fixed, straight, infinite line of current I1 is increasing at a rate given by gt squared, where g is a constant with the appropriate units. A second fixed rectangular loop containing a resistor R is vertically below the straight line of current such that the loop and the wire are in the same plane. There is no gravity. Find the force of the straight line of current. Whoa, what? Find the force of the straight line of current on the loop as a function of time. Whoa. What? So the reality is that this thing. Oh, so basically, oh my God, this problem is hard, dude. Because you got to use Faraday's law and you find the change in flux This gives you the induced current through here because you get the EMF. So are we given this B or is this induced? I think that's induced. But yeah, it's clearly in a two-step. No gravity. So, wait, let's first just apply Ampere's law. I Okay, so we found the magnetic field, away from here. And it's a function of time. Okay, the net force due to this. Sweet. Because I cross B. Okay, so that one's down. I cross. That one's up. So IL cross B. So they're both, the L is equal to, there's a L. Okay, it's L. That's fine. So B here, so R is going to be, so okay, wait, so F1, the top, so we have a loop going, but the thing is, we're not given these directions, so we don't actually know. The current could be going up there and down there. How do we know which direction the current is going? We know if the B field is going in, so see that the B field goes into the loop. The B field from I1 goes into the loop. So the induced EMF by Lenz's law oppose. So the current Okay, so yeah. So see that there's going to be a changing magnetic flux, and the flux is going to be increasing through this little patch of area. That is going to induce an EMF that is going to try to create a magnetic field in opposition to the change. So the change is increasing into the page, so we're going to have something increasing out of the page. So this is going to make a EMF that's going to turn this counterclockwise. Okay. All right, so now we know the EMF, and we know that this thing has a resistance, right? We have an R here. So then E, we need to find E. We don't know E, but we know its sense. We know what's going on with it, but we don't know what it is. But then we apply. Okay. Wow, this problem rules. There's so much at play here. Oh, this is a good one. Okay. Is there anything else we want to? Okay, so everything is in the same plane. Find the force of the current, the wire, the infinite wire current on the loop. First, see that by a quick Ampere's law, that the wire, the loop has B from the wire directed into the page. Also see that B is equal to GT squared over pi 2 pi r. Okay, great. Okay, so B is equal, so then dB. Oh wait, no, but that's not, no, it's the flux is B int B dot dA n hat, but n hat B minus K hat 2. So we're gonna get L B. Hello. What's going on? All right, so the area is LB, and that's not changing. So it's only the B that's changing. Uh, oh yeah. Why? Why am I? All right, um, so it's aligned. So cos 0 between B and and so the dot. Oh, but B, no, but you have to take this integral, so you can't pull it out. So you can pull out the L little b, but it's gonna be the integral. Wait. Hold on. Let me think about this. So B, um, okay. B is GT squared over pi r or 2 pi r. Um, dot. So this is directed minus k hat. Then we're gonna take the dot product of that with dA, which is gonna be LB minus k hat. Okay, so then we just have to take the integral of the product. But what are the bounds there? That's so weird. No. Yeah, you're not. No, you don't even have to take an integral. I think you don't even take the. I think you just get GT squared over pi. Or wait, let's say LB GT squared over 2 pi r. I'm pretty sure that this is the whole. So this is the flux. Flux. So now we just take the time derivative of the flux, and we're gonna get 2 GT LB over 2 pi r. Cancel the 2. GTLB over pi r. Okay, so then, the EMF is going to be equal to minus GTLB over pi r. What is r? Wait, the flux. No, something is super wrong. Because the flux can't be dependent. Um, I think, oh gosh, what do you have to do? You have to do, um, you probably need to integrate, R. No, but where do you get a dr from? Yes. Oh, man. That's where I'm missing it. Okay. Yeah, so I'm gonna do this problem on the board. Yeah, I got this far now. I forgot the L. I lost the L. Yeah. All right. Yeah. So let's because okay. So flux is equal to int mu0 g t squared over 2 pi r times LDR. So we're going to get mu 0 gt squared L over 2 pi integral 1 over r. Oh, but we need the bounds. It's going to be from a to a plus b, or dr. So the final thing is going to be mu 0 g t squared L log, or ln, a plus b over a over 2 pi. So here's the flux. So then d flux dt is equal to mu 0 g t L ln a plus b over a over pi. Let's write that down. Mu 0 g t L log a plus b over a over pi. So the negative of this is equal to the EMF. So that's the EMF, but we can just figure out the sense of it. So then is equal to I times R. So the current, so I is equal to, minus mu g t L log a plus b over a over pi R. All right, so now we have the current. Wait, did I even finish the last page? I guess I did. Okay. All right. Let's get rid of this. Okay. So ohms, so it's equal to EMF minus EMF. So find I via EMF equals IR. So I is equal to minus mu 0 g t L log a plus b over a. And this should really be a, but whatever, like, come on, pi r. Now, we want to know the force. Now, to find the force, we just do IL cross B twice. The sides will cancel. Because I think the sides will cancel. I'm not totally positive about that. So the current, holy cow. What is the direction of L? L top has L hat equal to minus dx I hat. Bottom has dx I hat. Alright, so let's just write it out. Alright, so what is the direction of the force? This is going to be I hat. So we're going to have I, J, K. Of course, the bottom one's going to win. So that's really the one that we care about. So it's going to be minus dx. And then B is directed K hat, minus K hat, so minus 1. So we should get minus J hat times dx, or something like that. Or just x. It's just x. So the force is in J. Wait, this was I. This is J. No. This is J, and this is K. Yeah, let's see if I got the problem right, because I really don't know about this one. So here's the flux. What the fuck is going on here? B1 and B2? What does that even mean? Okay, that makes sense. But why are they directed in... Oh. I1. Jeez Louise, that's insane. That problem is... This might be the hardest problem yet. What? Dude, I'm a student, bro. I'm a student trying to prepare for finals. I'm not... Our teacher provides us these answers so that we can figure out what the hell to do. All right, come on, let's start clean slate. We've got an infinite wire of current I. We've got a loop, a rectangular loop. Okay, this distance is A. This distance is B. This distance is L. The resistance here is R. The current as a function of time is equal to G times T squared. Okay, then we want to find, I think that's literally everything that we need to. The thing that I love about these physics problems is it takes so little time to describe the problem, and it's a very hard problem. Find the force of wire on loop. Okay, so first what we're going to do is find the B field. One, find B of R. Two, we're going to find the flux. Three, the EMF. Then once we have the EMF, we can apply. Then 4, we find the current. Find I loop, current loop. And then once we have the current loop, we should be able to find the force by IL cross B. I L, B. All right, so the first step is find B of R. So what we're going to do is draw an Amperian loop through some current, distance R away. So the closed line integral of the magnetic field B dot dl is going to be equal to the I enc mu 0. Now the enclosed current in that wire is given as gt squared mu 0. So that's the thing. Now by symmetry and dl is parallel with B everywhere, we can just do the B dl cos 0 integral. We're going to get B L, which is going to be 2 pi R, is equal to mu 0 gt squared. So B in our plane is equal to mu 0 gt squared over 2 pi R minus k hat. Now that we have the flux, or the B field, we need to find the flux. The flux is given by the surface integral B dot dA n hat. Now what is dA though? The integral of mu 0 gt squared. Is there a minus sign there? No, but n is minus k hat, so it's fine. Times 2 pi R times L dr. And then we're gonna integrate this flux from A to A plus B. This is gonna give us the flux, which is equal to mu 0 gt squared L log A plus B over A over 2 pi. Now we need the EMF. So, okay, so 1, we found B. 2, we found the flux. 3, it's going to be minus mu 0 gt times 2 L log over 2 pi. Okay, we found the current in the loop. Right. So then, ILB top plus ILB bot, and well, what's the sign of these forces? I mean, first off, okay, so current's going this way, B field's this way, so this one top is minus J hat, and bot is plus J hat. So this is going to be, but what current is this? This is loop. I loop L times B top minus B bot. And this is going to be, and then B top is going to be mu 0. Oh yeah, let's just do this. Mu 0. That is a really, really hard problem. So here, let me write the steps out. So 1, find B vec of R. 2, find flux. 3, find EMF. 4, I loop. 5, dang man, these problems are nasty. All right, 57. Amazing, very fun. All right, let's see. Do I still find it that way? Am I still going to find this problem fun? Consider the arrangement. So we have a loop, current I1. Then we have a rod, about a pivot. This distance is D. This distance is L. There's a consider the arrangement shown in the diagram. An infinite straight line of current I1 creates a magnetic field everywhere. A current segment L, don't worry about how it completes the circuit here, exists as shown. Okay, so there's an IS through this. Where it's hinged free vertically by through the point. Find the magnitude of the torque. of I on S. Okay. All right, so what do we know about torques? Torque is going to be equal to R cross F. But what is F? F needs to be an FB. So, okay, so first we're going to find all right, so in the direction here, let's make a coordinate system I, J, K. This is going to be minus K hat. Okay, so now we have B. Now 2. The angle between B and DL. So IDL cross B is equal to IDL B sine 90. This is 1. So do we need to use Biot-Savart? I think we do. I think you have to use Biot-Savart. So we're going to get or no, wait. Biot-Savart is to find the B field. What am I talking about? No, but we do need to do a integral. So we need to find the direction of, DL cross B. This is going to be J hat. Okay, so now R cross F is going to be, or DF rather. So what is R? R is going to be equal to, oh yeah, this is the weird part. This R is different from the B field R. So the B field R is R minus DI hat. So we're going to R minus DI hat cross D. Right, so I, J, K. Okay, so I think I found the thing. So tau is equal to the integral of it's going to have to be from d to d plus L of r minus d. Oh, and dl this becomes dr. But actually, wait, hold on. Let's see if we can just pull it out. So wait, we're going to get this can't be right. Wait, first off, B, no, because B depends on R, so this is all wrong. Wait, but what if I... No. This is going to be R minus D I dl times mu 0. So this is I. This I is going to be IS. Because for... Can you just move everything out? I1 IS mu 0 R minus D over 2 pi R times L. There's no way that's it. Yeah, so you have to... But how do you know? How do you know? It's because DL... Because R is going to change with DL. It's not as fun anymore. Oh, Refer to the diagram and find the magnetic field vector at the indicated point. Where is he even pointing, dude? This shit is so insane. Some of these diagrams are so bad. Okay. The total current is out of the paper and given as I, and it is uniform through the wire except for the hollow. The hollow continues through the wire as is shown. Consider the wire is very long and straight out of the page. So we need to find the B here. So what we're going to have to do is that 4/3 thing. So the current density. So we got to find the current density. So and what's the point? What is the point? So the area here is pi. Right? The current density is 3/4 pi r squared. No. The current density is going to be I divided by 3/4 pi r squared. Right, so the current through the I plus part of this thing. So then we can do an Amperian loop. So for, oh, but we needed, no wait, yeah. Find the magnetic field vector. So what is the magnetic? So this is the is equal to I think. So then the inner B dot dl is equal to, so we get 2 pi big R B is equal to, 4/3 I big R squared over 3R squared. And if the current is out of the page, we're looking this way, then it's got to curl around. So it's got to be this way, It's got to be, to say I hat, J hat, K hat. Man, I am slowing down. So now the negative part, the distance is R over 2. So B minus now is going to be equal to the current density should be 1/3, right? It should be, so I inc is equal to 1/3 I. So B dot DL, so B times 2 pi R over 2, this cancels, B pi R. Wait, no, I messed this up. This needs to be the radius R minus R over 2. I don't think I got this thing right. B squared minus A squared. Oh, you're not given that it's R over 2? I think I gotta call it. I'm not getting anything from this, man. How did this come about? 51. My God. Oh, wow. Wait, is it? I can do circuit problems. I can do circuit problems, I think, in my sleep. All right, let's do this thing. Resistor, cap, ground, resistor. This is R1, 10, R2, 20. Loops around. This is, what is that? V1, 10. Resistor R3, 30. Connect. Cap, C2. Source, V2, 20. Okay, so we're gonna just go around A, B, C, D, E, Is it 20 over 6 minus 20? Let's see. This is some 6. Or this is let's do 3. 10 over 3 minus 60 over 3. Yeah, cool. Yeah, these problems are pretty easy. I'm feeling a lot of these ones, they're just like, just recognize that there's only a single loop with current going through it. And once you see that, then the problem becomes like pretty easy. Yeah, they're not so bad. All right. Yeah. Again, just straightforward. Right. Single current loop. All right, I think that's gonna be it. Oh wait, which is this one? Oh, this one rules. I actually can do this one like that now. I figured it out. It's actually not that bad. Let's just look at a few now. Oh yeah, this one. Yeah, you have, what does this have? This is current through it. So how do you do it? You first you find the B field here, and then you need to do IF is equal to DF is equal to IDL cross B. B is always directed K hat, but DL is going to be, some sine cosine thing. And I think that's it. I mean, besides all the math, yeah. So yeah, he does this. Yeah, and then there's that. Okay. Obviously, just looking at a problem and saying I could do that is like dumb, but I feel like I could do that. Oh, this one is awesome. This is actually so cool. I love this one. All right, so here, uh, when it's open, no current flows at all, which means that R1 and R2, that there's no potential difference across here. So this is all one equipotential surface. And so then, V equals, what, C equals Q over V, but they're in parallel. I don't know how to deal with the parallel caps, but it should be, but yeah, so C1 is equal to Q1 over V, C2 is equal to Q2 over V. So the charge, Q1 equals C1V. So we're going to get V times C1 plus C2. So this is the charge open. Okay. And the charge closed, these become a serial resistor. And then you can just derive the you could do KVL, but you could find the drop. If you know the drop, then you know what the voltage is across C1 and the voltage is across C2, because these are in parallel, these are in parallel. And then you, given that you know the potential across both of these, then you just divide it. Yeah, I actually understand that one pretty good right now. All right, let's see. Find the electric potential at point A. All right, single thing, find this. Okay, so once you, all right, this is grounded. Actually, wait, hold on. Yeah, this one's a joke. That's not gonna happen. Something that easy is not gonna happen. Okay, apparently there's minor mistakes here, but I really need to practice these. I just hate this style of problem so much. I hate it because I don't understand it. This is a good one. This one's like the same as what we did. To the 1/4, 1/16. What? All right, I don't know this problem. There's so many left. All right, I have 2 more solid days to really do this, so there's not much time left. Find the electric potential at points B and A as indicated. All right, so there's no capacitors. So this is a serial parallel problem. So these two are in parallel. Wait, hold on. There's only 3 nodes. There's got to be a way to see what's going on here. These are actually not in parallel. However, these are in parallel. So we can make this 1. Right, let's try to do the reduction. Okay, so we return this into oh, and then we turn this into this. Then we make, okay, then we turn that into that. So then this goes into actually, I don't know how to do this one. I don't know how to do this one. Is it 16? Need to do that one. This one. Oh yeah, I've never done this one. Okay, this is a great one because All right, so we have a non-uniform current, so that means we are going to have a time varying magnetic flux through the loop. So that means there's going to be an induced EMF. So then what is it? Find the current, or not? Yeah, find the induced current. That's what I figured. All right, that's not so bad. I feel like that's a lot easier than the force one. The force one is a little crazier. I mean, this is still hard, but it's not like unbelievable. Okay. Two sources, no caps. Yeah. How do you see? So this is dead. So this is all one thing. So this is ground. So this is -10. We need to find this so that this is 5. So basically, in these star problems, I think the only way to do it is just use KCL. But I really got to drill the circuit problems because I'm not going to have time to, like, it's easy to get lost in those. By any valid method, find the induced EMF. Oh, shit. I don't like these. Find the induced EMF between the ends of the rod length L, moving with constant velocity V. Top of... Okay, wait. So V... So B is time... Or V is radius dependent. B is... What did I say? V? I meant B. But it's going to be into the page. So V cross B... The force is up. So FB is pulling this thing up. But is that what we want to know? We want to know the induced EMF. So if we know the force... No, see, that's the problem is you can't use the force. I don't think you can use the force on the rod to find... because you're going to have to do this weird thing of V dx. You know, what is the area? It's going to, it's going to be B dot dA. I don't get it. Oh, yeah. Oh, this is really good. Okay. Okay. 91's a good one. Using the Biot-Savart law. Oh, yeah, this one's nasty. But it's straightforward, but it's nasty. You know, some off-axis thing. But I guess this is like the second one I've seen, so he really wants us to get comfortable with this. So, what is that, a 3? What is that? 3? Or is that a Z? Oh, that's a Z prime. Okay. All right, just really nasty POS integral dB B. Oh, this looks different. Oh, okay. A circular region contains uniform magnetic field as shown in the diagram. Yeah, real nice diagram. Okay, here we go. B. I mean, it looks like we're looking down a solenoid. The magnetic field is increasing at a rate of dB dt. While this is occurring, at one instant of time, the magnetic field has value B0, and at the same instant, a charge plus Q is injected into the field with an initial velocity Vxi. He must give us a coordinate system. Okay, it's that way. This is I, this is J, and that's minus K. The distance from the center of the circular region that the charge is injected to is given as R. I mean, this is just the most insane diagram. Okay, I think I actually see. So this is like a. V cross B. It's going to be pointing straight up, right? So it's going to make a circle. In the reference frame of the charge itself, find the electric field E it experiences. A full formal use of unit vectors is required for full credit, and your final answer for the E prime field would be in terms of unit vectors as given in the diagram. Your final answer for the E field in the new frame would contain the given speed of the charge from the original frame. All inertial frames see the same Lorentz force. So does he just find E induced? But the fact that, what is he doing here? Why is he using Faraday's law? He has to use Faraday's law because the magnetic field is changing. Oh shit. Okay, this is like a absolutely need to do multiple times. Holy cow. Alright, this one seems easy. Consider the diagram. A charge Q of mass M is initially moving in a circle in the YZ plane due to the presence of a magnetic field B. Then a uniform magnetic field or electric field is applied in the positive x direction, causing it to in an expanding helix as shown. Find the horizontal distance along the x-axis the charge moves during the second period. That's okay. That's actually like not that hard. Because I think what you do is you find you just find the period, then you solve the kinematics for, x of 2t and x of t, and you subtract. I don't think that's that hard. Yeah, I mean, yeah, you could do this too. I mean, should still do it, but like that's not one I expect to really freak out about. Oh boy. Okay. All right. Okay. All right. Refer to the diagram. A single loop of rectangular coil current I is wrapped around the diameter. Why is it pointing there? Is wrapped around the diameter of a cylindrical drum of radius r. My hat? What? What? My hat, bro. J hat. My hat. I hat. Oh my god, bro. That's good stuff, man. My hat. That's funny. That's really good stuff. Okay, fine. Okay, so we have this loop. Is it only, does it go all the way around? It's got to go all the way around. It's got to go all the way around. There's a massless string wrapped around the drum with a mass M tied to it. Find the value of the current I such that the drum does not rotate. There is gravity in this problem, of course. Yeah, why would there not be? Although to find the magnetic moment vector of the loop, you can just use inspection methods. The rest of the problem must be worked using a full. Okay, so magnetic moment is going to be IA, right? So this is going to be, we're given D. So D, what is the radius of the drum? Radius R. So D times 2R times I. So mu is equal to D times 2RI. So then the torque, and this is, what direction is this? It's going this way. So it's minus K hat. Or he's probably, he made it, no, he made it minus I hat. So that's the magnetic moment. But then there's got to be a B field. We have a uniform B field. Okay, so mu cross B. That's a torque. Wait, mu cross B. Yeah, that's the torque. So if the torque of something is going this way, it's spinning this way, right? It's got to be, because this mass is going to pull it the other way. So we find the, the torque, B is uniform. So we're just going to get tau is equal to minus J hat D 2RI. This is minus I hat. Nah, but I did it by inspection. I'm good. So that's the torque. And then now we just need the R cross F. Does it matter that it's pulling from here versus here? That's actually a really interesting question. I'm going to guess that it doesn't matter. So then the torque is going to be, it's going to be, what is it? Big R cross F. This is minus mg. Minus RMG. J. What is it? It's not J hat. It's, what is that? It's minus K hat. So it's K hat R M G. But that's a no, but I didn't do the cross product right because wait, but that's the force. No. So the force, this is I hat, so it's gonna be I J K. This is gonna be minus R I hat 0 0. Then the force is in K hat, so it's gonna be 0 0 minus mg. So we're gonna get minus J hat times RMG. Right, so they're both minus, so something's wrong here with my torques. Because I'm getting that. Is it mg over 2di? Or, wait, where's B? The, B. Yeah, so I got it right, but there's a minus sign problem. Why isn't this I hat minus? Oh, because that is I hat. Okay. Alright. Alright, so this one's actually really easy. That one's not too bad. This is the real battery problem or what? Referring to the diagram, find the value of R load such that the voltage across points A and B. Find the value of R load such that the voltage across points A and B is 0. Real battery problem. I don't know about that. 37. Oh, yes. This is like the El Clasico one. But we got to find the terminal velocity. Yeah. Okay, need to do. All right, refer to the diagram of conducting rod. So basically what's happening is that the magnetic flux through here is changing. So you find the change in the magnetic flux, and that's going to be the EMF, the induced EMF. So this EMF, so B is coming through here, and it's increasing. So we're going to have current going around here like this. Yep, he drew it here, but I could figure that out myself. And what do we want to know? There's a connecting rod. There's no friction. All right, so we have to do this sine freaking stuff. I don't like the sine mg. Oh yeah, we looked at this. Did we not do this exact problem? I feel like we did this earlier. Maybe there's a duplicate. He just gave the exact same problem. But yeah, I mean, definitely do again. Now I'm just kind of spraying and praying. All right, these ones are There's gravity in this problem. A conducting rod. Oh, find the terminal velocity. Or no, find the rod velocity as a function of time. A conducting rod of mass m and length L completes a circuit. This is a great problem. I actually was thinking about this with gravity. That's cool. So it's going to be 1 minus x. Yeah, that's right. Yeah. A conducting rod of mass m and length L completes a circuit with the rod initially at rest. All right, so first we're going to just find... Well, what do we need to do? This is actually tricky. Okay, so we have this, right? This is given to us. It's got to be given to us. So I actually don't know how to do this. Okay, yeah. So what we know is the acceleration, but we don't know the... Or we know... Alright, need to do this one. Need... same shit. Find the magnitude of the force between two concentric loops of radius R1 and R2 carrying current I1 and I2. For the diagram, there should be an integral over d theta ready to integrate. That's pretty cool. That's weird. How do you do it? Because you have... Alright, Biot-Savart. But I don't think you could just use Biot-Savart. I think maybe there's a symmetry argument. I think you just use a symmetry argument. So you say, like... Alright, B times 2 pi r. Because we want to find the B field here, right? Why would this be into the page? That doesn't even... Or out of the page. That's not out of the page. That's not right. Yao is right. What? You really can't use... They're concentric. You can't... Actually, no, you can't use Ampere's law because there's no current piercing the loop that you make. So you can't do that. You know, if you drew an Amperian loop here, the enclosed current would be 0. So that's not going to work. Really need... Okay, definitely. Need... Or 90. I'm just trying to get a sense of just all of the problems. But really, I'm going to end this quite soon because I'm not getting, like... I'm not getting the like, learning. It's like I'm diminishing returns at this point. A rod of length L... Where's the pod? What the hell is this drawing? What is this and what is that?